Hey everybody, thanks for joining me. Today we are going to look at identifying linear, quadratic, and exponential functions. So the agenda is to complete the do now, which will be to read about functions modeling productivity. We're going to complete some class notes. I'm going to ask you to try the your turn problems. In this video, I am actually going to model problem number 4 in the your turn problems. Your homework is to finish the classwork, and then there's a hyperlink to slide 11 to try a few additional problems. So I would suggest at this point you stop the video so you can read the do now, functions modeling productivity about Tom, Sean, and Billy. When you're ready, restart the video and we can go through the class notes together. So the first function we're going to look at is the linear function, and we're going to look at it when it's represented in an equation, graph, and table. So when given an equation, the x should have an exponent of 1. That is how you know you have a linear function. So if you don't see the number 1, remember the phantom 1, it's x to the first degree. When you are given a graph, you are looking for a straight line, and that is how you know you have a linear function. Remember, it's going to go on forever and ever, so I'm just going to put those arrows to show you that it goes on forever and ever. In a table, you're looking for the first difference to be the same in the y values. So in the x values, I can see when I take those finite differences, from -2 to -1, I'm increasing by 1. From -1 to 0, plus 1. From 0 to 1, plus 1. And from 1 to 2, plus 1. And from 2 to 3, plus 1. In the y values, from -2 to 1, I'm increasing by 3. From 1 to 4, plus 3. From 4 to 7, plus 3. From 7 to 10, plus 3. And from 10 to 13, plus 3. So when I look at the finite differences in the y values, it's the same value. So I know it is a linear function because there is a constant rate of change. And you've heard me say this before, constant rate of change. And that's really important in a linear function. So again, in the equation, you're looking for the exponent to have a degree 1. In a graph, you're looking to make sure that the graph is a straight line. And in the table, you're looking for a constant rate of change. You're looking for that first difference in the y values to be the same. So I'm going to do a little extension. To find the constant rate of change, you take that finite difference or that change in the y value and you divide it by the change in the x value. And so I'm going to use a different symbol. I'm introducing a new symbol now. And so that symbol is change delta y divided by delta x. And so 3 divided by 1. And that is your constant rate of change, which equals 3. All right, now we're going to look at linear functions, quadratic functions, and we're going to look at the different representations. And so you know you have a quadratic function when the degree of the x is 2. That is the highest power. And when I say degree, it is a synonym for the exponent. When you look at the graph, you are looking for a U-shaped curve, and that is called a parabola. This one opens down. We saw in class the other day that sometimes these also open up. And when you are looking at a table, you're looking for the difference to be the same when you take that second finite difference. The same for the y values. So when we look at the x values, we can see that they are all increasing by 1. And I'm not going to go through this for all the values, but you can see they're all increasing by 1. When I look at the y values, to go from 9 to 1, that's a decrease of 8. And to go from 1 to -3, that's a decrease of 4. From -3 to -3, there's no change. From -3 to 1, that's an increase of 4. And from 1 to 9, that's an increase of 8. So I do not see the y values being the same when I took that first difference. So I know it's not linear. So I'm going to try the second difference. So to go from -8 to -4, that is an increase of 4. To go from -4 to 0, that's an increase of 4. To go from 0 to 4, that's an increase of 4. And to go from 4 to 8, that's an increase of 4. So I see that second difference is constant in the y's, and that is how I know I have a quadratic function. So again, when I have an equation, I'm looking for the highest power in the x to be 2. When I have a graph, I'm looking for a U-shaped curve called a parabola. And in the table, I'm looking for that second difference to be constant in the y values. So the last function we're going to look at is the exponential function. This is different than the other functions, or really any other function you're going to look at, in that the independent variable is the exponent. So you're going to see the x in the exponent right here. So graphically, you're going to see that the graph will rise or fall very quickly. And again, I'm going to put little arrows. So this one is decreasing. So this might be something radioactive that's decreasing. And then here's something that's increasing really quickly. And that would be perhaps population, or we talked about like COVID, something being growing very, very quickly. So in a table, we're looking for the common ratio to a ratio is something, when you think ratio, you should think multiplicative relationship in the y values. So if I look at the x table again, I can see that all my x values are increasing by 1. These are the same input values for all the examples. When I look at the y values, I can see when I'm going from 1/4 to 1/2, I'm increasing by 1/4. 1/2 to 1, I'm increasing by 1/2. 1 to 2, that's +1. 2 to 4, that's +2. And from 4 to 8, that's +4. So I don't see a constant value in my y's. So now I'm going to take that second difference. To go from 1/4 to 1/2, that's an increase of 1/4. From 1/2 to 1, that's an increase of 1/2. From 1 to 2, that's an increase of 1. And from 2 to 4, that's an increase of 2. So I don't see the second difference being constant in the y values. So I do not see that this is a linear or quadratic function. So now I have to look for a different relationship in the y values. And so I'm going to look to see if there's something that I could multiply by to make 2. Well, that'd be 2, right? So instead of looking for something to multiply, what I'm going to do is I'm going to take that ratio, okay? So the ratio, and I'll start with something that's easy. The ratio of 8 to 4 is 2, right? The ratio from 2 to 4, that was also 2. From 1 to 2, that was also 2. And if I take the ratio of a half to a fourth, remember that's a complex fraction, and we can write that as 1/2 divided by 1/4. And now it doesn't look so complex. And remember, complex fraction is a fraction with a fraction in the numerator and or denominator. So once I write it out as horizontally, I see it's not so bad at all. And if you remember, for dividing, you keep, change, flip. And so I see that common ratio of 2. So the common ratio is times 2. So I multiply each of these terms by 2. So an exponential function, I'm looking for the x value in the exponent. I'm looking for a graph that will really rise quickly or fall very quickly. And in a table, I'm looking for a multiplicative relationship there, a constant ratio. And I can get that just by taking the ratio of consecutive y values to find that ratio. So I'm going to have you try the your turn problems. The first part is pretty straightforward. You're just going to identify, when given an equation representation, what type of function it is. In the second part, when you're given a graph, to identify what type of function it is. In the table, again, you're looking for the finite differences, or you're looking for a ratio to determine what type of function it is. And the application problem is the one I actually want to do with you. And it says to use the data in the table to describe how clothing stores' sales are changing. And then we need to determine if it is linear, quadratic, or exponential. And then we're going to do an extension. We're going to actually write a model that could be used to make a prediction. And that is really the beauty of math. It helps us make sense of our world. It models phenomena that we see in the world, and it can help us make predictions about the future. So I can see that the independent variable is year. The dependent variable is sales, because the sales depends on what year you're talking about. So when I look at the year, I can see that they're all increasing by 1. And when I look at the sales, I can see that it's increasing from 15,000 to 15,750 by 750. And that next finite difference, again, plus 750. And then from 16,500 to 17,250 plus 750. So I can see that there's a constant rate of change, and this is indeed a linear model. So to get that constant rate of change, we're going to take that ratio, or that change in our sales. So our change in our y divided by our change in our x, which is 750 divided by 1. So I'm going to describe this as linear, because there is a constant rate of change. Now, a linear function, there's different representations. And one way to represent a linear function is something called slope-intercept form. And so slope-intercept form is y equals mx plus b. And m is our constant rate of change, or our slope. And remember, I abbreviate it CROC, or slope. Our b is our y-intercept. It's where the function crosses the y-axis, which means your x value would be 0. So when we look in the table, we can see the y-intercept is right here. And we have our slope. So I'm going to substitute that in. Y equals 750x plus 15,000. And that is a function that would model this data. This is a huge extension. This is not on the test. But again, I hope you're starting to get used to my teaching style. We started talking about so many of the ideas that I'm formally introducing now classes ago, so that when we got here, it wasn't your first exposure. Because I know so many of these ideas are new, and the more you hear them and are introduced to them before you formally look at them, the better off you're going to be. Okay, so what do I expect you to be able to do? Identify this as a linear function, because you can see that the first difference is 750. And that means there's a constant rate of change. It's linear. Everything else I'm doing right now is that extension, and it's your first introduction. So stick with me. I'm really proud of you. Okay, so now we're going to use our function to predict the amount of sales after 10 years. So after 10 years, so we're going to say after 10 years, x equals 10. What's that going to look like? Well, we're going to sub it into our equation. Y equals 750 times 10 plus 15,000. All right, so I hope you know just to tack on a 0 when you multiply by 10. So that's 7,500 plus 15,000. And so I'm going to just do the math over here. 15,000 plus 7,500, 22,500. And that is my prediction. After 10 years, the sales should be about 22,500. All right, great job, everybody. Thank you for watching this video. I hope you found it helpful. Please reach out to me with any questions that you have. Thank you.